Welcome to Quantum Curious, and in today's video, I'm going to discuss a theorem related to purification as purification we discussed in the previous lecture, and I will also discuss the applications related to quantum entanglement. So in the previous lecture, we discussed what is purification, and we showed that how can we form a purified state using another basis and a reduced state that is we know and it is a mixed state. So what kind of freedom we have in order to form a pure larger state from a reduced state? So this statement and this kind of freedom is stated by Uhlmann's theorem. And we will also show that what kind of applications uh, can be built using quantum entanglement. So consider we have a purified state or we have a reduced state rho A, and we want to form uh, another state that is a pure state and it is a larger state. So we have to use another basis from the system say B, and we have state rho A, that is a reduced state. So what kind of freedom we have in order to form this purification using some basis B? So we discussed that we can use any kind of basis as far uh, as long as uh, they belong to this to the eigenstate or eigenspace of system P, and we know that the basis in the eigenspace in the basis in the eigenspace are related to unitarily to each other. So we showed that this is the freedom we have, and the Uhlmann's theorem states that this is the only freedom we have in order to form purification. So consider we have psi AP and phi AP. These are two states, and they are both a purification of state rho A, that is a mixed state. And Ullmann's theorem states that they are the purification of the state of rho A as long as they are unitarily related to each other. So we have only this degree of freedom, and it is a unitary degree of freedom. So it can be shown by an example. So consider we have two states in their Schmidt decomposition, and we have lambda I and mu I as the Schmidt coefficients. So we know that state rho A is a mixed state, and we want to form a purified state or a purification by using the system B. So we know that lambda I is an eigenvalue of reduced state. So we know that both the eigenvalues should be the same because the state is same. So lambda I should be equal to mu I. And we know that uh, if the eigenvalues are same and we are considering that we have non-degenerate state, means uh, the eigenstate or eigenstate has only one eigenvalue, or in other words, eigenvalue is related to only one state. We can see that the the two states ui and w, they are both equal and of the normal basis of system A. So we can form any purification using using states or orthonormal basis from system B, and we know that the basis or eigens vectors from eigenspace from the same eigenspace should be unitarily related to each other. So both the systems, both the states are both the orthonormal bases are related to each other by a unitary transformation. So this is the Ullmann's theorem, and it states that this is the only freedom we have in order to choose some a basis to form purification of any state. So next we will discuss the applications of entanglement. So we know that we have four orthonormal bases, and these are called Bell states, and these are orthonormal bases of the space of the two qubit system. So we can check that they are orthonormal to each other by using inner product. And one insightful point and remark is that the reduced state of all these states uh, is maximally mixed state. So if we take some kind of trans uh, trace over a system, say B, the reduced state is going to be maximally mixed state. So this is going to be for all the uh, for all the Bell states. So we can get some kind of uh, important and significant result that we know uh, globally what the system is, but we do not know uh, or do not have that much information about a local state. So this can be used for many applications. So first of the applications is secret sharing. So we want to distribute a secret so that no authorized party can learn it. So uh, one of the interesting story behind is that consider we have a country, and this country is a nuclear state, and it has a nuclear weapon, and nuclear weapon has to be operated with some kind of code. So we want to make the code very secret. So we have the queen of a country called Alice, and a king of a country, or this country, king of this country is called Bob. So to in order to uh, nuclear bomb to be installed uh, with the agreement of these two, king and queen, we can share some kind of secret bit uh, to each of them, and they do not know uh, about the whole bit. So in order to uh, launch a nuclear weapon on another country, they have to both share their uh, local secret in order to get the global secret and the code to launch the nuclear weapon. So that is from this story uh, we can explain or understand these kind of scenario. So this is the classical scenario we want to achieve, and we want to achieve through a quantum scheme. So what could be the quantum scheme behind this? So consider we have secret bit A and B, and uh, both the bits are needed to get a complete secret, and we can encode this secret into Bell basis. So we can see that we can encode the secret in Bell basis, and A and B could be 0 and or 1. So we are encoding the secret in Bell basis, and both the Alice and basis have one qubit. Mean it means that they have reduced state, and we know that reduced state is going to be maximally mixed state. So they do not know priori that what kind of entangled state they are sharing. So they come to they come close to each other and implement a joint Bell measurement uh, on their individual qubits. So after knowing the results, that is the A and B, they can infer that what kind of entangled state they are sharing. And So after knowing A and B, they can infer that what kind of entangled state they are showing and they can recover the whole secret quite easily and secretly. So this is a very good and simple example using quantum entanglement and the application of it. So another important application of entanglement is superdense coding. So we want to transfer some secret to Bob using only one qubit. And we want to, and so our goal is to send two classical qubits using only one qubit. And this could be done by a shared entanglement. So consider we have a state that is the first Bell state, and Alice wants to send some kind of um, bit or some kind of so Alice wants to share two classical bits to Bob secretly. So Alice wants that he she wants to use some kind of resource that should be very minimum, and we can show that the resource could be a maximally entangled state. So consider Alice wants to send 00, that is the two bits to Bob. So in order to send it, she can employ a unitary operator on the entangled state. And in that case, the unitary operator is going to be unitary or identical or unit operator. So in that case, the maximally entangled state is not going to be changed. Or Alice wants to send 0 and 1. In that case, she is going to operate with a unitary operator, and that unitary operator is going to be a, a not uh, a not operation, and also called X operation on her bit. So that operation is going to be implemented on her qubit. So if she wants to send 10 state 10 message to Bob, she can send her qubit in and her qubit operated with a Z basis or Z operator. And if she wants to send uh, the bits 1 1, she can send uh, the bits 1 1 by sharing her qubit with Bob, uh, and her qubit will be operated with X and Z operator simultaneously. So after sharing the after sharing her bit with Bob, Bob is going to implement bell measurement, and after bell measurement, he will know that in which uh, global state the two qubits are. And uh, after knowing that suppose the Bell measurement result says that the global state is in psi 10. So Bob will know that Alice wants to send the message 10 uh, to him. So that is an efficient way to send a two qubit or a two classical bits to Bob using only one qubit, and that qubit is coming from Alice. So we have another interesting theorem that we are not going that we not want that we are not going to explain in that video is that Halaba's theorem. Halaba's theorem states that uh, we can send or we can uh, exchange only one classical bit using a qubit. So we know that a qubit uh, is a uh, two-dimensional state, and it lives in an Hilbert space of two dimensions. So it is encoded with, or you can say that it has two values, or it is in a superposition state of two states. So it should have two bits of information. But Halaba's theorem states that we can only record one bit by employing measurements. So on implying measurement, we will get only one bit, or we will know only one bit uh, after doing measurement. So consider we have a state, you can say in a superposition of 0 and 1. So after measuring that bit in some basis, we will only know the one result. So that is the Halaba's theorem, and it states that we can only recover one classical bit from a qubit. So that is for today. So we discussed what is Uhlmann's theorem, and we discussed two applications related to quantum entanglement. That is the secret showing and superdense coding.